I will take over. Let's see here. Share the screen. Okay, maybe give me a thumbs up or something if you can see my screen. Okay.
We can see it.
Okay, cool. Awesome. Thank you very much, Timo. As he said, within the first hour, we will be up and running and doing our first models. But before we get started, I'd like to ask you to take a second and think about probability. What is probability? What does it mean? What do you understand if somebody asks you the probability that you're going to be on time, for example? Or what is the probability that it will rain tomorrow? Over the next 2 days, we're going to be thinking about the notion of probability and how to define it in light of the research that we do. A key reason why we talk about probability has to do with frequentism, right? You might have heard of this term before, but if not, that's fine. I'm certain that you already have a grasp of what it is, given everyone's background that's here today. Over the next few days, we're going to be thinking a lot about frequentism and comparing it directly with Bayesianism or Bayesian methods. So what is that? Frequentist statistics represent what most of us have always been doing or have been doing since we started learning statistics. It's a bit of a blanket term to refer to classical statistics. And the frequentist view of probability is what leads to some of the odd definitions in the non-intuitive statistical machinery that you probably already know, like confidence intervals, for example. And a key idea is that population parameters, what we estimate when we do statistics, are fixed and that they actually exist, right? And under this view, probability refers to the long-run frequency of any given event. So we can consider a sample of data as the result of one of an infinite number of exactly repeated experiments, right? And in this sense, the data are random, and the result from sampling the result is from sampling a fixed population distribution. Okay, so the key idea that I'd like you to keep in mind at this point is that this view of probability seems to be at odds with how we normally think and how we reason. For example, when we ask something like, what is the probability it will rain tomorrow? We aren't typically thinking about long-term frequencies or exactly repeated experiments. So we're going to come back to these ideas and we're going to be thinking about probability and frequentism. But for now, consider this. What if there isn't one true population parameter, as I just explained? What if instead there's an entire distribution of parameters and some of them are more plausible than other ones, right? That is the fundamental idea behind the Bayesian inference that we're going to be talking about today. One key idea that I'd like you to hold on to for right now as well is that Bayesian inference is all about what we're going to call the posterior distribution or posterior distribution, depending on how you decide to pronounce it. I'm going to spend the rest of my time in this short session building up a little bit of intuition about what the posterior is, okay? In other words, in Bayesian data analysis, we produce or we approximate a posterior distribution of possible parameters that we can then summarize in different ways to answer questions and to quantify our uncertainty about a given hypothesis. And this is a fundamental difference with regard to frequentism. In other words, there is no posterior distribution when you do frequency statistics. You only estimate a single value of a parameter, all right? And I'm going to walk you through applying this idea to regression, which is what we're assuming that everybody has experience with. So as many of us already know, in a standard linear regression in a frequentist framework, we typically estimate what we call a line of best fit. We can use ordinary least squares or maximum likelihood estimation, but it's quite simple. The idea at its core, we have a blob of data and basically we're just going to try to stick a line through it to describe it the best that we can, right? Under a Bayesian framework, we derive a distribution of lines, not just one best fit line, a distribution of lines that are compatible with our data and our prior assumptions about the data. Some of these lines are more plausible than other ones, so we can use standard methods to summarize and quantify our uncertainty about them. So I'm going to give a brief illustration to try to make this idea a little bit more clear. Here we see a scatter plot that represents a traditional linear regression with a line of best fit with some reasonable margin of error around it in a separate color. And if we plot next to this, the most plausible line from a Bayesian regression, we can see that essentially it's the same thing. Essentially, we see the same line, it's the same data. Here we can plot the most plausible line, and also along with that, 20 random draws of plausible lines that fit the assumptions that we made about the model and the data. We can also do the same thing, but we could plot 50 random draws of plausible lines. Or in this case, we could plot 200 random draws of plausible lines. Now, you probably are noticing that we seem to converge on the same result, even though we're not expressing our best guess of a true regression line. Instead, what we're expressing in the Bayesian analysis is uncertainty about the relationship by plotting the posterior distribution of lines that are compatible with our assumptions and the data. The orange line merely represents the line that appears most often in the posterior, right? That means that we can assume it to be a more plausible outcome. Now we're going to build our first model in just a second, but first let's get to know the data set that we're going to be using. You can continue following along on the slides, or I'm actually just going to do this in RStudio. So let me just open that up real quick. Probably should have done that beforehand, but that's okay. And let's see, let me make this a little bit bigger. Now, if you want to, you can just sit back and watch this, or you could also kind of live code along with me, whatever you feel like doing. But to get started, let's go ahead and we will open the learnB4SS package. Works for me, that is good. And also we will load the library BRMS, which is the package that we will be using to fit all of our models. Now, if we use the data function and call polite, we can see the data set that we will be using for the rest of the workshop. This data set comes from a study by Bodo Winter, 2012, where he was looking at the effect of politeness on realization of pitch. Timo talked about that just a minute ago. Now, we can see that if I like to use the glimpse function. Let's try this. We'll run this on the data set. And I spelled it wrong. Oh, no, I forgot to load the tidyverse. Let's load one more package here, just to make things easier. There we go. You can use the glimpse function, or you can use the stir function if you're not using tidyverse. It doesn't really matter. And we can take a look here, and we can see that we have a data frame that has 224 observations. There's 27 columns that represent the different variables that we have. And you can just kind of take a look, scroll through here and see that there's a whole bunch of interesting things. Obviously, they were looking at pitch, so we have measures of F0. What we're going to do for right now is we're going to play with the articulation rate variable. So what I'm going to do is I can just do a couple simple functions here. We'll go polite $sign to get that specific vector, and we will say articulation rate. And I'm just going to copy this because I'm going to do it a couple different times. And we can learn a little bit about this data set. We can see that the minimum value is about 3.3 syllables per second, and the maximum is around 12 syllables per second. Let's get a quick and dirty picture of what this looks like. We'll make a histogram using the hist function. Oh, margin too long. I have to make this bigger and run it again. Just a second. There we go. And we can see it. It looks like it might be slightly skewed in one direction, but we do see the extreme values that I just mentioned before. So kind of close to normally distributed. We can run simple function like mean, right, to get the mean of the distribution. We see here that that is about 6.68. We'll go ahead and remember that because that's going to be important in just a minute. We could look at the standard deviation, for example, about 1.16. That's the measure of spread around the mean. We could even use the quantile function, and we can get, let's see, put the same thing here. Will be prob equals 0.025 and 0.975. We can look at the probability at certain quantiles in the data, for example, at 2.5 and 97.5. I'm kind of hinting at getting towards a confidence interval. Anyways, we just can play with this and get a glimpse of what's going on with the data set. I'm actually going to just paste what I just did into the chat. If anyone is following around, but maybe they can't see that or I'm going fast, you could just copy and paste that if you wanted to into your RStudio if you're following along. If not, that's fine. We've got a feel for what the data set looks like. And as I said, we're going to continue playing with this over the course of today and tomorrow. Now what I'm going to do is let's go ahead and fit a model. And I'm going to call this F mod 00. The F in this case implies frequentist, because we're going to do a standard linear regression here with a frequentist framework. So we'll look at articulation rate, and we're going to build an intercept only model. So intercept 1, and we'll call our data polite. Let me just make sure I have a little bit of space here. Okay, So what is an intercept only model is pretty much the simplest model that we could start with. It's only going to fit an intercept to the data, and it's assuming that there's no slope or a slope of 0. I can fit this model, and then I will call summary on it to take a look. F mod 0, 0. Make a little bit more space here. And if I send the summary to the console, this is the line that I want to call your attention to. We see that we did estimate a parameter for the intercept, and the value is 6.68. You might recall when we looked at the mean of the data set, that's what we got as well. So whenever we fit an intercept only model, it's actually just giving us the mean of the distribution. And then if you want, you can look at the p-value, which tells us a test of independence that tells us basically that this value is significantly different from 0. Awesome. So there we go with our frequentist model. Now we're going to just do the exact same thing, but we're going to fit a Bayesian model. So I'm going to call this B mod 0, 0, in this case, the B for Bayesian. We're going to use the BRM function, right? And then I'm going to just fit the exact same thing. You could just copy and paste it if you want, but this is going to be an intercept only model again on the polite data set. And I'm just going to use all of the default settings in this function. I'm not going to do anything else. Go ahead and run that. If you're following along, you'll notice that it says compiling Stan program. If you don't know, Stan is, actually, I don't do that. Stan is a probabilistic programming language that we're going to use. It's kind of what's going on in the background for fitting all of these models. So basically it's translating into Stan language, and then it's going to fit the model, and then it's going to spit the data, the results back out to us. So what we'll see in just a minute is that there's a sampling procedure. There it was. If you were looking, you saw it really quickly. If you're following along, you're seeing it on your computer, but we can see there's all these chains and iterations and crazy things going on. And over the course of the next 2 days, we're going to explain what all of that means. But for right now, what I'm going to do is I'm just going to send this to the console and take a look at the output. Let me make this a bit wider.
Hey, Joe, real quick,
yes.
just interrupt. So first of all, for everyone, we have some issues with the Q&A tool. It somehow times out after a really short period of time, so we can't really use it. So please type in Zoom chat for now. That makes things obviously difficult for us to keep track of it, but we will do our best. The other thing is there are a couple of people already, especially now that people were looking for a Q&A tool. They struggle a little bit for following along, Joe. Let them give people a little time to code along to get their own model going. Yeah, let's hope that works a little better for people. Sorry about the technical hiccups, folks. We were not aware.
Yeah, and again, I just pasted everything that I just coded into the chat again, and I'm not actually going to code anymore. That's the end of that. So you guys should be up to date with that if you want to copy and paste it. Okay. Anything else, Timo?
No, beautiful.
Okay, awesome. So if you guys are saying things in the chat, I can't see that, but someone will let me know if it's important and I need to stop real quick. So I sent this to the console, and now I can see the output of the model. And actually just going to focus again on one line. The population level effects is what it says. And we can see again, we have an estimate of the intercept. You'll see that the value is the same one that we saw before, right? And then there's some other stuff here that we're going to worry about later. It also estimated in a parameter for sigma, which is the standard deviation of the articulation rate data. And let me just run this other one before, just so you can see that it was the same 6.68 and 6.68. Now, this is all cool. I've basically shown you what I just showed you before in plots, which is that essentially we can get the same, we can come to the same conclusion, we get the same result. But what it doesn't show us is what's really the cool part about doing a Bayesian analysis, which is the posterior distribution, which I mentioned before. So what I'm going to do now is I'm going to use a function called posterior samples. And then I'm going to stick the model in here. So B mod 0, 0. Let me make this a little bit wider. Right. And what this does is it takes our model and it extracts from it the posterior distribution of whatever we just fit. So you can go ahead and do that if you want. I'm actually going to go back to my slides now and show you the rest there because it's already programmed in there too. So these next couple of slides are basically just going to show you what I was just doing. Here's a look at the data frame. Here's the distribution, calculate some descriptive statistics. We fit our first model. We looked at the output. So we already saw all this. So at this point, you're saying, okay, what's the difference? So what? Why do I want to do this? The main takeaway from everything that I'm showing you right now in this first session is basically the posterior distribution. Like this is what we get when we make a switch from frequentist statistics to Bayesian framework. So I can turn the model object into a data frame that has 4,000 samples of the posterior distribution. That's 4,000 plausible values for the intercept that I estimated, and also the standard deviation. And that's what you are seeing right here in this screen. And that's what you saw when I used the posterior samples function before. Now, we can use all of the mathematical tricks that we know to describe the posterior distribution in any way that we find meaningful. For example, you can take the mean of this posterior distribution, which I do here, and you can see that the value is 6.678, which if we round up is 6.68. Again, it's the value we saw from fitting the model previously. You could also calculate a credible interval. I used the quantile function before, and I'm doing the same thing here. We're saying, okay, with 95% confidence, we're sure that this estimate of the mean falls within this range. I will talk more about credible intervals later on. Not too important for right now. But the point is that we can use whatever we want to describe the posterior distribution. It's just a distribution like any other distribution, right? Here I'm using a forest plot to describe the posterior distribution of the two model parameters in a single plot. This is a handy way to summarize a model. A key takeaway here is that when you see the peak of these distributions right here, those represents the values that are most common in the distribution. So those are the ones that we could think of as being the most plausible. Here's a scatter plot of the entire posterior. So this is 4,000 samples. And this is a handy way to visualize the posterior parameter space. We'll talk about that tomorrow, because it emphasizes the fact that we're looking at a two-dimensional space, a joint probability distribution, and that there are many estimates for the intercept parameter and the standard deviation parameters that we estimated that are essentially the same, right? We have a lot of estimates that appear often similarly, they're repeated, and that implies that these are values that are more plausible, okay? I've highlighted the most plausible combination of the intercept and the sigma, the standard deviation, by putting the medians of each of those in the orangish point that's in the middle there, right? We can think of the joint distribution as a mountain, it's a hill, and the orange point just represents the highest point. So you could think of this as like a mountain or a hill, and maybe we're in an airplane and we're flying over the top looking down on it, right? Here's another way we could see the same thing if we looked at this with a heat map, where the lightest colors represent the highest point of our mountain, which means it's the most plausible value. It's the most plausible one because it's the one that appears the most often in our distribution. And if we tilt this ever so slightly, we can see it in 3 dimensions, and then it makes it a little bit more easy to understand that we're looking at a little hill, a little mountain here. So I'm gonna start to close here, but I wanna leave you with a couple ideas. So there are 2 primary camps in statistics. We talk about frequentists and Bayesians, typically. The 2 camps see probability in different ways, right? Frequentists think that parameters are real, they're true, and we try to provide our best estimate of whatever parameter we're estimating. And Bayesians, on the other hand, think of distributions of possible parameters, and we summarize these distributions, right? The main idea is that for Bayesian statistics, it's all about the posterior. That's where we're doing something, the main thing that's different from when we take a frequentist standpoint on these things. So with this in mind, you are now on your way to becoming Bayesians. You're young Jedis that you've got your lightsabers and you're dangerous. And over the next couple of days, we're gonna be building intuitions around these core ideas and have you on your journey. That is it for me, Timo and Steph, for this first session.
Thanks, Joseph.
What is up next?
We have a break next, but I will briefly answer a couple of questions, especially about the live coding. Maybe you can put Yoda away for a second.
Yeah, sorry, let me get rid of Yoda real quick.
Yeah, so one thing that came up in the chat, and again, sorry about the hiccup about with the Q&A tool. We have found another tool. And so people were really confused that your model, Joe, took a couple seconds to compile and to sample, while other people had to wait quite a bit, right? And we will talk about at the end of the day today, Bayesian modeling and the sampling procedure in the background is computationally very expensive. It can take a while, depending on your computational power. So this is totally normal, right? That it might take longer for some than others. Joseph or Stefano, can you mute yourself real quick? Yeah, thanks. The typing was really loud. And then there's another thing that people ask, and that's probably important to point to, is that someone posted their posterior mean into chat and said, look, this number is not the same number as Joseph's number. And that is correct, because there's a random component to the sampling procedure. So if you don't specify a particular initial state, initial value, when the random sampling starts, you might all have slightly different results at the end. They're really, really tiny, just tiny different, but there might be differences, right? So that is, and we talk about that later, where we usually want to specify a seed that fixes this initial state and that creates the exact same result. Steph, do you want to add a couple of questions and answers?
Yeah, so let me see. There's lots of questions about the computing time. So perhaps, do you want to say something about that? Or?
I just did.
Good. Sorry, I'm doing, like, as you all can imagine, I'm doing 100 things at the same time, but I only have a tiny brain. Another question that came during the first Q&A question was this. I'm going to read it out loud. One thing that I haven't yet grasped is why null hypothesis testing is fundamentally weird and not intuitive. I see this as a burden of proof problem. Isn't the burden of proof on the researcher to provide evidence of something? This seems to be what null hypothesis testing does.
Absolutely. This goes really deep, and I'll try to give you just a shallow answer. I was Chris, I think. Yeah, that is exactly what null hypothesis testing does. That is not what we want to do, though. I wanna speculate. I want to know whether a certain hypothesis is probable or not, whether a certain value is probable or not. I'm not interested in disproving a null hypothesis. I want to estimate possible values, plausible values, and want to get an estimate of how certain I can be that this value is actually true, given what I have observed in the data. It's a different philosophical stance. Absolutely, and the weirdness is not. The weirdness is maybe I'm using that, kind of casually in pointing out that the weirdness is in the logic is very far from how we usually draw probabilistic conclusions in the real life. That is why it's a little weird, and I think people misinterpret what a confidence interval, what a p-value, what a model estimate actually can tell you. And that's why I say it's weird. But you're right, it does what it's supposed to do. I'm contesting and say that's probably not what we want to do. But that's that probably goes too far. I'm happy to chat about that off the record. And I think we should take a break. There was a lot already. Maybe 15 minutes break for all of us. Maybe you can have a look at the code again that Joseph posted in the chat and try to run it on your machine. And we will reconvene at 4:15, okay?
Well, 15 minutes from now, whatever your time zone is.
Yeah, 15 past, yeah, in 15 minutes, okay?
I will, in the meantime, I'll try to answer some of the small questions on Slido. So if you asked a question, you can check that out. Okay, so yeah, see you in 15.